object at rest, I put a charge at rest in the presence of another charge, its energy, the potential energy will drop as it starts to move towards or away from the other object. Now, I'm not going to derive it for you. Sorry about that. If you really are anxious to, bring out the calculus, do that derivation. Actually, would you like to see the derivation? Getting two people shaking their head no, but a lot of people with just not moving one way or the other. I'm assuming the people who did not speak want to see it. Someday. The formula. I guess you're just gonna have to trust me then. The electric potential energy formula is that the electrostatic constant, or Coulomb's constant, times Q1 times Q2 divided by R. Just a single R, not R squared. And there's a good chance at some point I'll put the R squared at the bottom just out of habit, but for energy it should just be an R. So if Q1 and Q2 are both positive or both negative, what does that tell you about this formula? If Q1 and Q2 are the same sign, what can you tell me about that potential energy?
It's positive.
Yeah, it's gotta be. So if Q1, the sign of Q1 equals the sign of Q2, the electric potential energy is, I don't know where 0 is coming from, is positive. If they're opposite signs, yeah. So I got a positive charge here, and into that I stick a positive charge. Now we know from the electric field explanation and from the force explanation that this charge right here is going to be forced that way. So let's see, so R is that distance right there. Let's come up with some numbers that work really nicely there. Well, the electrostatic constant is 9 times 10 to the 9th newtons meter squared per Coulomb squared. Let's make Q1 equal to 4.5 times 10 to the, oh, that's not right. You know what, Q1 and Q2, let's just set up Q1 times Q2, we're gonna set equal to 24. So our K sub C, Q1, Q2, just make equal to 24, and that would be Newton meter squared. It'll save time, so I don't have to think about what Q1 and Q2 are. So if my two positive charges here are 1 meter apart, what is the electric potential energy?
Joules?
Yes. If they are 2 meters apart, what is the potential energy? Yeah. Yep, there we go. Because my numerator right here, I'm just plugging, it's a plug and chuck. The numerator I said was 24, and we're just dividing by whatever R is. So notice that as the positive charge moved farther away from the first one, my potential energy dropped. Since the electric force is conservative, my kinetic energy increased, so it's moving away. So as my denominator gets bigger, my potential energy gets smaller. Yes,
How do
Jason?
you determine what's Q in the problem?
It's usually given to you.
Okay.
In 110, it'd be given to you.
So why don't we multiply the 9 times 10 into the 9 with 24?
Because I said that the whole thing multiplied together was 24.
Okay.
That I was trying to think of a Q1 and Q2 so it would come out nicely like that, and then I thought it's just easier just to, whatever Q1 and Q2 are, if I multiply all of it together, I get 24. All right, so big questions at this point, because I'm gonna ask a question that will stump people for a moment. Or maybe not this group. If I got a positive charge and a negative charge, we know what's gonna happen. We got two other explanations for it. What will happen? All right, I've seen a couple hand gestures there. We'll just go with it. They will be attracted to each other. But I really care about just the negative charge there, so let's just concentrate on that. So what's happening to R as the negative charge approaches?
Decreasing.
Now, I thought if I had a fraction here, and the denominator gets smaller, doesn't the fraction get bigger?
Yeah.
So if my potential energy is increasing, that means my kinetic energy has to decrease. But if this started at rest, it can't decrease, unless somehow it magically becomes negative mass or imaginary speed. So there seems to be a conflict. So let's go back to here. As R gets bigger, no, as R gets smaller, the fraction gets bigger. Is that true? I think that was a nod of there. Jason's willing to go out on record. And now that I said his name has been recorded, we all know. If you'd like me to bleep your name, I can do that. Well, let's see if that makes any sense here. So here I have 24 over 1 is 24. Actually, let's start big. Let's start at 6 there. So if it's 6 meters away, that this would be 4. 24 over 3 is 8. 24 over 2 is 12, and 24 over 1 is 24. So my denominator is getting smaller, but the fraction gets bigger, so that seems to match. But I know the negative charge is going to be forced to the left. The potential energy has to be getting smaller, but R is getting smaller. How do we resolve that? Or perhaps the question is, when does making a denominator smaller make the fraction smaller?
When the numerator is getting smaller too.
But the numerator is pretty much constant unless you're
Same.
changing the laws of physics. Part of the Q continuum. How many people caught that reference? Go with the Q continuum. About one person. Well, thank you.
You've got a negative.
If that's negative 24, negative 24, negative 24, negative 24, this starts out at negative 4, and then it goes to negative 8, then negative 12, and negative 24. Which one's bigger, negative 4 or negative 8? Did I ask which one's bigger?
Yes.
Okay, yeah, the negative 4 is. So if this is negative, as R gets smaller, the fraction gets smaller. Well, if they are opposite signs, that numerator will be negative. And so, it works out that as they get closer, since the numerator is negative, as they get closer, let me cap this before I accidentally write on the board. Opposite signs, numerator is negative. As r gets smaller, the fraction gets smaller, gets more negative. And so kinetic energy goes up. That's three explanations for why the negative charge would be attracted to the positive charge. Let's write that out a little bit more formally or succinctly. Let's write it out. All right, so that's the electric field explanation. If an object starts at rest, its kinetic energy is 0. If it is forced by a conservative force, to start moving, kinetic energy goes up and potential energy goes down. If two charges are same sign, the electric potential energy is positive. This electric potential energy goes down if R goes up. R being the distance between them. If two charges are opposite signs, the electric potential energy is negative. This electric potential energy goes down if R goes down. Questions to hear, or give people a chance to write it, then I'll ask it again. And I wonder if I wanted one of those concrete blocks with it, they'd just give it to me. Imagine my wife's delight when I came home with one of those. It's okay, I'll put it in my office. I picked her tears. All right, any questions? All right, so now we have 3 explanations for the exact same thing. But wait, there's more. Sort of capture what we have so far. If I have a single charge, that's single charge, and I'm talking about vectors, I'm dealing with electric field. The formula, that electrostatic constant times the charge divided by R squared, R hat. Oh, we didn't talk about units. How dare we? What do you suppose, if you flip back through your notes and, yeah, not really there anymore. Oh, but it's bound to be, do I have it over here? this. What would the units be? Remember, we got this formula by taking the force formula and getting rid of one of the charges. Mathematically divide by one of the charges.
Newton meter over coulombs?
One too many words.
Newton meters?
Wrong one.
Newtons over coulombs?
Yeah, newtons per coulomb. So the units of the electric field, the SI units. A newton per coulomb. So we've nailed that explanation about why electric field explains why things attract or repel. If I have two charges, and I'm dealing with vectors, I have a force. And the formula case, let's see, electric force 1 on 2, Q1, Q2, over R squared, R2 at. Let's make it formal. What would be the SI units of this?
Newton meters squared.
Stop. Okay, start again and then stop quickly.
Newtons.
There we go, stop. It's a force, newtons. K has the units of Newton meter squared per coulomb squared. The coulomb squared would be canceled out by these coulombs here, and R would cancel out, the R squared would cancel out the meter squared. Badly worded, but you got the spirit of what I'm going with there. And then we talked about if I have two charges, but I'm dealing with scalar, we're dealing with potential energy here. And the formula, Kc, Q1, Q2, over R. And the SI units here. What are the SI units of electric potential energy? Apparently, chapter 7 had a huge impact on your lives. We reframed the question.
Is it joules?
Yes, there we go. Just joules. We obviously have a hole there. So if I've got my electric field from my force by just getting rid of a Q, well, if I have a single charge scalar, why don't I just get rid of a Q here, and I'll just do Kc over Q, or KCQ divided by R. You okay? Now, I'm not gonna put what it's equal to yet in terms of the symbol, because I want to lead into that, because unfortunately, it's another one of those places where a little bit, if they'd spent another 5 minutes thinking about it, they could have come up with something better. This is known as electric potential. This is electric potential energy. They are related, but they are not the same thing. At this point, if I now say, hey, what's the potential? I'm talking about this. There's still kinetic energy. I should say, and the recording, so I probably could go back if desired to figure out how often I messed up on this. But if I'm talking about potential energy, I actually need to use the word energy. All right, the units of electric potential. Well, if all I did was take my potential energy and get rid of a charge, what do you suppose the units are of my electric potential?
Joules. Joules?
Are you stopping there?
I was planning on it.
It's, the relationship is similar to what we have up here. This was newtons, and then we got rid of a charge.
Over coulombs.
Yeah, I think you just said it. So the units here, SI units, would be a joule per coulomb. It's supposed to be a capital C. Now, joule per coulomb is too much. Physicists look at that and they're going, do I have to write all those letters? And they said, no. Let's come up with a one word. The volt. So a joule per coulomb is a volt. Named after? That tends to be the pattern, but it actually is volta. Apparently, the A was too much for them also, so they decided just to drop it. All right, so it is the volt. So now the symbol that, where I said if they'd spent 5 minutes more, they could have come up with something better. The symbol for electric potential is a capital V. So, if you have V is equal to 2V, those V's represent two different things. This V is the electric potential. This V, the one after the number, is volt. Really wish they had not done this, but they did, and we're stuck with it. Until one of you gets into a position of power to change it, we're sort of living with it. Now, we have not talked about voltage yet. Voltage is related, but it is not anything that I have on the board yet. Because why make it so simple? Questions to hear before we talk about voltage?